Today we are going to just focus on the few shot learning of the LLM. So whether it is few shot fine-tuning or few shot in context learning, we are going to see like pros and cons of different training frameworks, and also we are able to see whether the few shot fine-tuning is it really that expensive, and maybe it will save you the cost in the end with the fine-tuning part than just in-context learning. Uh, Before we diving deep into that paper, I want to first just give an overview of the LLM training paradigm. So the usually to train the LLM, it starts with the pre-training, right? So the pre-training is trained on a large corpus of data. This data are usually like enabled, unsupervised training, right? So you just do kind of the next word token prediction on trillions of tokens for the pre-training part. So this part is just to learn automatically about the languages, the grammars, the basic reasonings in the pre-training. For example, if you see some like open source models, they usually release a pre-trained model like for example, the Llama 3 70B. And then they will also release a fine-tuned version of the model that is fine-tuned on multiple labeled data sets. So after the pre-training, there's usually a multitask instruction fine-tuning. So this will be a relatively fine-tuned on a small label data set. Well, when I say small here, it's comparable comparing to the pre-training data sets. It's small, but still it can be big. It can come from like a multiple task, and it may be like reaches like millions of training samples in the instruction fine-tuning. And people also do some like human preference alignment with the reinforcement learning. So this is comparable wise training. Well, given two outputs from the LM, it asks prompt the human to say which output you like most. I think if you use the ChatGPT, you also see that sometimes it will generate two outputs concurrently, right? And then it asks you for feedback. And then after taking the feedback, they are going to just to retrain the model to align better with the human preference. I put it here, it's like I think this step is optional, depending on what specific task you're on. If it's like a chatbot and human preference is very important, then this step is essential to get there, to better align with the human preference. So these are the kind of what needs to happen before we kind of have the access to it and we try to adapt it to our use cases, right? And then when we want to use LM for specific use cases, it usually comes into two framework. Like one is just in-context learning. There's no weights update. You just provide the examples like input output pair as the in-context examples in the LLM prompt, right? So you provide the task instructions. You also provide the in-context few short examples in the prompt, and hopefully the LLM kind of know, okay, what this task is about. How can I generate predict the right outcome given a query example. So that's in-context learning. There's also another, you can also like further fine-tune the model, although the model is already fine-tuned, right? So this is kind of the pre-fine-tuning of the model on as many as tasks as possible. While this fine-tuning will just focus on the task, the custom task at hand that you want to adapt it to. So this will requires a weights update, and because this custom data, the label data, it will be even fewer, much fewer than the previous like a pre-fine-tuning samples. It usually like varies from tens or up to thousands of training samples for the custom task. right? And so people have developing the parameter efficient fine tuning to further adapt the LLM to the custom task at hand. So this is the paradigm, and I think in this session we are mainly going to compare this few shot fine tuning and few shot in context learning. In terms of so this is an example of the few shot in context learning. So just in addition to the task description, you also provide a few example of the task, right? So the task description is like do this translation, and then you provide, for example, three examples over here, translating English to French, and then you give your prompt for hopefully like the answer, the LLM can generate the right answer to the query to this input, right? So this is like in-context learning, no gradient updates. The model stays the same. The only changes is a prompt, and then the model may give like different answers according to different prompts. The few shot fine tuning is like fine tuning. I think we all know like it will involves adjusting the pre-trained model weights to better adapt to the new task. Because so this is different from in context learning because it requires additional training compute and memories so that you can update the model weights for your custom data. And one very popular techniques in the fine tuning is the LoRa model. I think I have also given a meetup on the LoRa. Feel free to check our recordings earlier. So the key ideas of LoRa is we want to learn low rank adaptations of the weights, right? So we just want to learn about the deltas of the ways that we want to make the changes to the original matrices in the LLM. So we just focus on a low rank representation where the low rank can be represented by a much smaller dimension matrices of B and A so that you can recover the delta matrices, which are the changes to the original matrices in the LLM weights. There are a family of path methods. And I will say the paper we are going to read today provides another way of how we want to do path. And it's also going to compare with other nine path methods, including the LoRa fine-tuning. I also want to list what are the pros and cons of the ICL in context learning and the parameter efficient fine tuning methods. So ICL, I think the pros is clear, right? So it just enables like one single model, one service to perform different tasks without additional training. So it looks like very convenient, right? So you just deploy one model, one API, one service, and then the users can just write their own prompts and provide different examples, and then they will try to adapt the same model to different tasks. I think that's how current or all the kind of ChatGPT like services is provided. I mean, if they don't apply to disclose their fine-tuning services, they may need just disclose like a one API or one chatbot interfaces, right? So for the users to write different prompts. The cons of the ICLs is the inference time actually will increase if you provide more in-context examples, and also the inference cost will increase. I think most of the APIs will charge based on how many input tokens you query the LLM and also the number of output tokens, right, of the LLM. So if you are going to include a lot of in-context examples, you are likely to increase your inference cost per query to the LLM. And usually comparing the performance, the in-context learning produces inferior performance compared to the fine-tuning version. Fine-tuning is usually the upper bound you can get. So usually it's like a fine-tuning is like what is the best maximum performance you can get with the data, custom data you have. So the ICL usually comes at a cost of yes, you can launch it quickly, but it may not as good as the fine-tuned version. And also, I think it still stays as a mystery of how the prompt can affect the model's reasoning, because like the formatting of the prompts, even the ordering of the examples may have a significant impact on the final outcome of the model. So I think that mechanisms of exactly how the model will or the best way to it's another world of research of how to come up with the best prompts or generate the prompts automatically to optimize the performance of the ICLs. Yeah. So in terms of the path, I think the pros is there's no additional inference cost comparing to the regional pre-trained model, right? Because it's kind of the same model. Also depending on what path adapters you use. Usually there's no additional inference cost, and because you don't increase your prompting your prompts, right? So you can skip all these in-context examples. You just fine-tune the model with all the examples, and then at inference time, it basically stays the same of the inference cost. And yes, it has the benefits of better performance compared to the ICLs. The cons of it, of course, is the one-time investment cost to fine-tune the model. Uh, it may be cons based on like your budget, but also we are going to show in the paper that it may be not that as expensive as you thought. So this is a paper we will focus today. The title is like few shot paths, like parameter efficient fine-tuning is better and cheaper than in-context learning. It sounds a little bit counterintuitive in the beginning because I think, majority just think that in-context learning maybe is the most efficient and cheaper than the fine-tuning one, right? This paper is published in LIPS 2022, and is highly cited so far. And this paper introduced IA3. So IA stands for infused adapters by inhibiting and amplifying inner activations. Well, if you put it in simple words, this is like you want just to decrease or increase the magnitude of the inner activations of your network. Uh, and it argued that the path is better than ICL in the few-shot settings, both performance-wise and compute-wise. I think it's among the first papers to answer like whether the path-like methods can work well when you only have like very limited label data for the training, for the fine-tuning. So I think this paper is kind of the first few, maybe just the first. It's the first paper try to answer this question to test out if you have, say, just tens of examples, maybe like from 10 to 70 examples, whether the path methods can still work. This is an overview of the IA3 method. So here, this is a diagram. I think the major contribution from this paper is introducing a new path adapters, the IA3, and also introduces additional loss functions on top of the cross entropy loss, the language modeling loss. In the IA3, so this you see this is the attention, kind of the attention calculation, right? So the keys, queries, and values. Well, the attention, you just multiply keys and queries, and then you weighted average of the values. What is the changes over here is it applies this LV and LK. So you can think of it as as the scaling factors of the elements in the matrices, right? So this is just doing element-wise scaling. Well, these scaling factors is going to be learned from that few short examples. So it basically adds these learnable weights to the GPT module. And also it's going to apply another scaling factors to the activations, which means this is the linear layer, and it will applies to after you go through the nonlinear, for example, the sigmoid, right? So the nonlinear activation function, it will applies to the outputs of the activation functions, the scaling factor to the output of the linear functions. So this is the changes. So the IA is just about how you want to scale the VK matrices and how you want to scale the outputs of the activations from the I think it use the encoder decoder. So any attention based architectures, you can apply these tricks to these values keys and activation matrices. It also introduced additional cost. So the cost includes the language model modeling, so which is the next token prediction, and also it adds in the unlikelihood loss. Basically, it passing the incorrect answer and want to minimize the likelihood of those incorrect sequence outputs. And it also adds a length normalization. So basically just to incorporate both the correct sequence and incorrect sequence for the length normalization. So I will tell a little bit more in detail next. This paper is developed on a pre-trained model, T0. So T0 is derived from T5. I have also conducted a meetup on T5. It's an encoder-decoder model. And T0 mainly focus on the zero-shot generalization. That's why it's called zero over here. So the idea is they want to train the T5 model on a variety of different tasks, like summarization task, sentiment task, question answering task. It's a multitask instruction fine-tuning. And you want to see whether it can improve the zero-shot generalization on the new task. For example, here is like a new task that it doesn't exist before in the multitask training, whether it can still generalize to the new task over there. So this is the T0 focus. Uh, so T0 is based on T5. It's an encoder-decoder transformer model. And it was created by further fine-tuning the T5 model on the multi-task mixture of data. And its goal is mainly focused on zero-shot generalization. And T0 is released in 3 billion and 11 billion parameters. So it's usually referred to as T0 3B or just T0. If you see T0, it's 11 billion parameters. T0 shows zero-shot task generalizations on English and outperforming GPT-3 at that time. Like GPT-3 is like 175 billion models on many tasks, while it is only like 16 times smaller in 2022. uh, so this is so basically after they choose a pre-trained model, and then they are going to make changes to the pre-trained model, right? So one change is they want to incorporate additional loss. So this is usually the objective to train the LLM is just the language modeling loss of predicting the likelihood of the next token probabilities, and it's trying to minimize the cross entropy loss for this. And in their paper, they also introduce additional loss, which is the unlikelihood loss. So basically here you see the hat over here. So this y hat, you also see a y minus, right? So this probability is kind of the sequence, the y hat sequence comes from the incorrect target sequences. So basically they choose n incorrect target sequences, and then they're trying to minimize the probabilities of these incorrect sequences. That's why you see a 1 minus this over here, right? So you still want to minimize this cost. So you want this to be as close to 1 as possible. So this incorrect probabilities should be goes to 0, as close to 0 as possible. Right, so it not just target the correct sequence, but also want to minimize the loss for the incorrect sequence. And also it add an additional normalization to combine the correct sequences and incorrect sequences. Well, this is basically just the language modeling cross entropy loss. It's the same formula, and it just do a soft max over it. So this is your correct entropy. This is your correct entropy. this is your incorrect entropy, right? So if you want to minimize this, you want this to be as one as possible. So you want to increase the cross entropy or you want to increase the probabilities for the correct sequences while minimizing the incorrect ones. So it applies this additional log probability of the correct answer choice by combining the correct sequences and incorrect sequences together. To be honest, I look at the result. I'm not sure like whether this is 100% needed. It based on tasks. Some tasks, it may even hurt the for performance, but some tasks it does show improvements over there. So that's the first. What is the training loss objective to fine-tune the LLM? And then they make some changes to the architecture, right? How we want to efficiently fine-tune the LLM with just tens of examples. So their idea is just to reintroduce the rescaling vectors on the keys and values, as I introduced already in the diagram shown earlier. And they also applied it to the intermediate activations of the feed-forward network. Right? So they apply these scaling vectors to the keys, scaling vectors to the values, and the self-attention mechanism is still the same. And then they also apply it to the output. So this is you can think of this as a sigmoid, right? So it's kind of just a nonlinear activation function or ReLU, right? And then basically you just apply a scaling factors on the output of the nonlinear activations. So these are the tunable parameters in the T0 um, architecture that they are going to fine tune on the few shot examples. Before we show some results, I also to briefly touch on the other Taft method. So in their paper, they compare with other 9 Taft methods, including all of this. So it's like basically it's like overall speaking, Taft is depends on like what set of parameters you want to fine tune in the network. It's not possible that you want to fully fine tune. Of course, you can also fully fine tune it. But but in order to save cost, right, to save the computing cost, we want to select just a subset of parameters to update, right? So these are just different strategies of how you want to uh, choose what set of parameters to fine tune. So some will just choose the best in the linear layers. Some will be this adding these additional layers, adapters. And some will be learn different embeddings of the prompt. So different different task may have a different prompt embeddings that will be concatenated into the model's input. And also we have talked about the LoRa last time that focus on the low rank updates to the parameter matrices. Right. So of course, they will also compare it with the full model fine-tuning with all those examples. Let's look at some of the results. I think some of the findings is also quite interesting, especially in terms of the cost, the training cost and the inference cost. So yeah, so as I mentioned, the evaluation done is on the T0 model. And each data set tested, the number of few shot examples vary from 20 to 70. So it's like, yeah, very small data set for the fine tuning. Because they want to match the same numbers as the few shot in-context learning. So basically, these are the few shot examples that also provided. You also can choose just to provide these few short examples to the context, right? And as I would say, then that would be a fair comparison if that context can hold this as many examples in the context, right? And then it will be a fair comparison of say a context containing 20 examples versus the LM trained with those fine-tuned with those 20 sample examples. On the evaluation datasets, I think there are mainly two datasets. So two categories of datasets. So one category, so it's based on the natural language understanding, right? For example, in the sentence completion. So all these datasets about sentence completion dataset. And of course, like this sentence completion is formulated into a multi-choice problem. For example, this is the context, and then the question is what happened as a result, and then you give like two likely answers, and then prompt the LLM to choose which is the likely result from this. And there can be co-reference resolution, like you want to figure out, okay, I, my, and she refers to the same person, right? And then he and this refers to the same person. So this is a co-reference resolution. There is also natural language inference. Yeah, so this is like, again, you provided some stories, context, and then the phone rang, right? And then you ask like who is likely to call Taylor? And again, it's a multi-choice problem. And also the word sense disambiguation. For example, the window, it may refer to the physical window, or it can also refer to the operating system Windows, right? And then based on the context given, what the Windows refers to. So this kind of tests how the LM is able to understand the context and make the right choice. So this is the result. So these are all the data sets from the task I previously mentioned. And then they compare the T-Few. T-Few is this paper, is this one. Uh, so this T0 is the pre-trained model, right? So these are the regional model without the path with a few examples. So this is a regional model. This is also the T5 is even the prior versions of T0, right? And then there will be a different versions of GPT-3 with varying sizes. And then all of these numbers is kind of like in-context learning, all of this is kind of like in-context learning examples, and they want to see, okay, whether the few shot fine-tuning can improve the performance, right? So first we need to verify that. If the performance is not equivalent or better, then there's no point to discuss what is the cost of computing over there. So basically, across all these benchmarks, they claim that with this future of fine tuning, they see a large majority, I would say, majority they see a large improvements of the performance for this task. Except for these two benchmarks, like although yeah, so it's like not beating the really large like a GPT-3. Somehow this data set is just not performing well for the functional fine-tuning. And this one I think is close, right? It's like 74 versus 77. I think this one is close. And for this one, I specifically look at, okay, what this data set is about. Is like this. I think it's quite challenging. So basically, it's like you need to have some common sense. It's not just like the context provided is not sufficient. You need to have some common sense. You need to have some physics understanding, so that you can choose the right answer. So maybe that's why it's just a drawback of the pre-trained model that is not has the knowledge of all the common sense over there. So maybe that's why it fails at this benchmark. Okay. And then they discuss about the inference compute and training compute measured in flops. So this is again comparing to the inference one. Of course, the T-Few will be the cheapest over here. It will exactly has the same as T0. Um, for the inference. The training, it will has this additional training, right? So this is the training cost estimated. It may involve additional disk. So this is the disk space to save those scaling vectors, right? So you see this this model introduce new adapters and they learn all those new scaling vectors. So this is basically this is the size of that. And this is the few shot examples. So for this model, for different tasks, they need to store the few shot examples separately. So of course, it will be a much smaller size comparing to the scaling vectors over here. And the T-Few, on average, it has much better performance comparing to the few shot learnings. What is more interesting is T-Few, the training cost. If you look at this, comparing it to the GPT-3, the largest GPT-3. So this is only 20 times comparing to this, right? So if you multiply it by 20, you get roughly this, which means that the training cost of the few shot fine-tuning it's just as running, you just call GPT-3 20 times on 20 examples, right? And the more inference you are run, the more cost you are going to save with this few shot fine-tuning version of the model, which is counterintuitive. So, but the key point is that using the path methods, using the adapter-based method, maybe it's the fine-tuning is not as that expensive, especially if you want to, if you want the best performance and if you want to optimize the inference compute, maybe the future fine-tuning is the choice to go. So the training cost is not as big as you thought, right? So this, yeah, basically this is how they come up with the training cost. Although it's not small, but this is just the 20 times cost comparing to the few shot in context inference using the largest GPT-3. Yeah, so this cost as much is the same as much as using GPT-3 to process 20 queries with few shot ICLs. And also in their examples, they fine-tune T0 on these single data sets. So the single data sets vary from 20 to 70 examples per task. Takes about an hour on a single A100 GPU, and it would cost about just $2 using, for example, using Azure for just to adapter fine-tune this model. They have run some ablation study on the effects of pre-training and losses. So loss, I think we understand because they introduce additional loss, right? So the unlikelihood of the incorrect sequences and the length normalization loss. So all of this is like minors. If we don't fine tune with this loss, what is the performance? So they want to measure the impact of of introducing this additional loss. They also tried pre-training. Pre-training is like they pre-train the new parameters using the same multi-task mixture of the T0 to pre-train these new parameters instead of just setting them up like randomly for the fine-tuning. So they also see some benefits, right? So if you do not pre-train those new vectors, you see some loss of the performance is about from 1% to up to 3%-ish here. Uh, yeah, so overall, I think they measures, okay, what step is necessary, what loss will gives you the benefits. And it seems like using the pre-training and with all these different losses, it helps on some of the majority of these data sets. And uh, they another benchmark they have used to compare the path methods is the raft benchmark. So this is a benchmark. Majority focus is on the few shot task. I don't know whether there's other few shot benchmarks, but I think this benchmark is like very helpful if you want just to compare the path methods, want to compare benchmark against the few shot performance. And the raft methods, all of them are classification tasks. And each task has the instructions. For example, this is the task instructions. And then it will going to provide you 5 training examples per task. So for each of the tasks, we are providing 50 labels over there. And these are like a different task descriptions over here. So some is based on label the sentence below to see whether it is related to an adverse drug effect. And given the banking customer service query classified into one of the following 77 classes, it's a lot of classes, etc., etc. So these are all classification tasks. And so these are the list of the data. They put it over there. And whether it is like a long inputs, especially if the task requires long instructions, whether it is domain expertise required for this, whether detailed instructions are provided. And for these classifications, what is the number of classes for this different task? Beyond the 51, right? So there are like a 50 training examples. There's also like a big test set, unlabeled. So for each of the tasks, they also have like a big test set over there. So in the raft, what is more interesting is they have the human baseline. Because we know like human cannot be 100% accurate, right? Especially if you ask a human to classify a banking query into 77 classes. I doubt the human performance on that. Um, so so it's very interesting that they use, I think this the human baseline is from the raft paper. It's not from this paper, but as human baseline is established for this raft benchmark. Basically, they just do a crowdsourcing and then they do the majority vote of 5 labelers as a ground truth. And then they use the ground truth labels to evaluate the human labelers individually. And then you get your human baselines over here. Uh, and before T-Few methods, without this few shot fine-tuning, all of this previous method has some gap on these benchmarks that not beating the human performance. And T-Few is the first method at that time to beat the human performance. Basically, like on average, it has this 2% more accuracy gain on top of the human baselines. And it is the first method to outperform the human baseline. And also comparing to the second place that time, it achieves like over 6% higher accuracy than the second best. So yeah, I think it's very interesting findings on this. And if you look into the details of how are these methods, so one natural questions coming to my mind is how is this proposal, how is this few shot fine-tuning, also called IA3 over here, how is it compared to other path methods, as I mentioned, right? So there are other 9 popular path methods, along with a few full model fine-tuning. And this is the number of parameters you need to update for the fine-tuning. So as you can tell, this one, prompt tuning has the smallest set of parameters, but this one I think is still small comparing to, for example, comparing to the LoRa one. And it has the best performance across like, I think this is about 4 for 11 tasks. It wins over 8 out of the 11. And for the others, like LoRa wins, right? So it's has only about 0.2 or up to 1% gap comparing to the LoRa fine-tuning. Yeah. So that's the ablation study. They studied the effects of the pre-training different loss functions. And then they also do this ablation study to compare to other path methods on this raft few shot benchmarks. I want to conclude of what is the main message of this meetup. I want you all to walk away with some learnings and with some messages you got today. And so this paper, like T-Few, um, it may need to show that the fine-tuning, few-shot fine-tuning can attain higher accuracy comparing to the few-shot in-context learning. And also it provides a new perspective of how we can perform the few-shot learning with large language models. Especially it has very good performance on the Raft, the few-shot classification benchmark, and they are able to improve over the human baselines for the first time. And also it estimates what is the inference cost and the training cost. And actually, the training cost, the inference cost has a lot of advantages comparing to the ICLs because the input prompts are much shorter, right? You don't need to include those examples in the prompt. And the training cost actually is not as big as you thought. It's almost equivalent to the 20 you just run the zero shot, the few shot GPT-3 20 times. The caveat of this paper I see is like all of these experiments is on multi-choices and classification tasks. I don't think it has fully explored and evaluated on the generative tasks, such as summarizations and Q&As. This paper also mentioned that they are also very interested to use this idea to test some more generative tasks. Yeah, thank you. That is for today. And I also want to refer to several our previous meetups related to this one so that you can have a good understanding of all the other branches related to this one, including the T5, since the T0 is derived from T5. So understanding T5 will kind of help understand T0. And also we have a meetup just focused on pre-training, instruction fine-tuning, and reinforcement learning with human feedback. We have also talked about GPT-3 since the GPT-3 model is one of the major in-context learning baseline in this paper. So if you want to understand more on GPT-3, you can look at this. And last time we have mainly talked about this LoRa and QLoRa. I think this is still the most popular adapter fine-tuning methods nowadays. So yeah, so this is another way of how you can do few shot fine-tuning of the LLMs as also as listed out as one of the baselines in this paper. Yeah. So yeah, I think these are all related previous meetups. If you are interested, go ahead and learn about that. And I'm also going to upload today's recordings to the same channel.